Once we have frames drawn on our kinematic diagrams, the next step on the way to getting the homogeneous transformation matrix is to create the DH parameter table. The DH parameter table records all of the displacement and rotation relationships between each pair of frames. The DH parameter table is a table that has one fewer rows than we have frames, because we have one row for each pair of frames. The table has 4 columns, one for each parameter. These 4 parameters include everything we need to express both the displacement and the rotation between 2 frames. So if we know these parameters for each pair of frames, then we can get the homogeneous transformation matrix directly. Here's how it works. 2 of the parameters record rotations, and 2 parameters record displacements. I am going to define each one at a time and give an example for each to help you understand what the parameter means. The 4 parameters are theta, alpha, r, and d. Theta and alpha are rotation parameters, and r and d are displacement parameters. Suppose we have 2 frames that are next to each other, like frame 0 and frame 1, or frame 1 and frame 2, or something like that. Since this could apply to any 2 frames that are next to each other, I'm going to call these 2 frames frame n and frame n-1. Theta is the amount that we have to rotate frame n-1 around the axis zn-1 in order to get axis xn-1 to match the axis xn. Also, we have to include in this parameter any rotation of the joint if the joint is a revolute joint, because this rotation is also a rotation around the axis zn-1. Let's try to understand this parameter better by looking at an example. Here's the kinematic diagram we drew in the last video. Here we have 4 frames, so we need to have 3 rows in our parameter table. We also have 4 columns, one for each parameter. The first 2 parameters are the rotational parameters, theta and alpha. The rows are labeled for the value of n, so we have 1, 2, and 3. Let's apply the definition of theta to the first row here. We'll substitute n equals 1 because this is row number 1. Theta then is the amount that we have to rotate frame 0 around the axis z0 in order to get axis x0 to match axis x1. In our diagram, x0 is pointing to the right, and x1 is also pointing to the right. So we don't have to rotate frame 0 at all in order to get axis x0 to match axis x1. Let's write 0 here. But wait, there's one more thing for theta. We have to also include in this parameter any rotation of the joint if the joint is a revolute joint, because this rotation is also a rotation around z0. The rotation here is theta 1. So we have to add that to this parameter here. The theta parameter for the first row is 0 plus theta 1, or just theta 1. Let's do theta for the next row. Here, n equals 2, because this is the second row of the table. So theta is the amount that we have to rotate frame 1 around axis z1 in order to get axis x1 to match axis x2. Here, x1 is pointing to the right, and x2 is pointing up. In order to get x1 to match x2, we will need to rotate frame 1 90 degrees. But should that be a positive 90 degrees or a negative 90 degrees? The axis we are rotating around is Z1, and Z1 is pointing out of the page towards us. Using your right hand, point your thumb towards yourself and look at what direction your fingers curl. They curl around counterclockwise, which is the same direction that we have to rotate x1 in order to get it to match x2. So the 90-degree rotation is positive. I am going to write 90 here. But wait, there's one more thing for theta. We also have to include in this parameter any rotation of the joint, if the joint is a revolute joint, because this rotation is also a rotation around Z1. So I need to add on theta 2 here. Now let's do theta for the last row. Here n equals 3 because this is the third row of the table. So theta is the amount that we have to rotate frame 2 around the axis Z2 in order to get axis X2 to match axis X3. Axis X2 is pointing up and axis X3 is pointing towards us out of the page. So we need to rotate X2 90 degrees to get it to match. But should that be positive or negative? To find out, we put our right hand thumb in the direction of Z2 to the right. The direction our fingers curl is the same direction that we want to rotate X2. It's towards us. So the 90 is positive. I'm going to write 90 here. But wait, there's one more thing for theta. We also have to include in this parameter any rotation of the joint if the joint is a revolute joint. But this joint isn't a revolute joint. So the 90 that we wrote is all we have here. Alright, let's move on to the second parameter, which is also a rotational parameter. It's called alpha. Alpha is the amount that we have to rotate frame n-1 around axis xn to get axis zn-1 to match zn. Let's do an example with the same kinematic diagram. For the first row, we substitute n equals 1. So alpha 1 is the amount that we have to rotate frame 0 around the axis x1 in order to get z0 to match z1. This is a little bit tricky because you have to remember that the axis we're rotating around is x1, not x0. But the frame that we're rotating is frame 0, not frame 1. So, for example, z0 is pointing up and z1 is pointing out of the page towards us. So we have to rotate frame 0 90 degrees to get z0 to match z1. But should this be a positive 90 or a negative 90? To find out, we put our thumb in the direction of x1 and we look at the direction our fingers curl. Our fingers curl towards us, out of the page, and that is the direction that we have to rotate z0 in order to get it to match z1. So the 90 degrees is positive, and I'll put positive 90 in this place in the table. Next, let's look at alpha for the second row. Since this is the second row, I'll substitute n equals 2. Alpha here is the amount that we have to rotate frame 1 around the axis x2 in order to get axis z1 to match axis z2. z1 is coming out of the page towards us, and z2 is pointing to the right. So we need to rotate frame 1 90 degrees in order to get z1 to match z2. So should this be a positive or a negative 90? We take our right hand and we put our thumb in the direction of x2, pointing up. And we look at the direction that our fingers curl. our fingers curl around to the right. That is the direction that we need to move Z1 in order to get it to match Z2. So the 90 degrees here is positive. Now let's look at alpha for the third row. For the third row, I'll substitute n equals 3. Alpha is now the amount that we have to rotate frame 2 around the axis x3 in order to get Z2 to match Z3. Z2 is pointing to the right and Z3 is also pointing to the right. So we don't have to rotate frame 2 at all in order to get these two axes to match. So I'll put 0 in here for alpha in the third row. Let's move on to our first displacement parameter, r. Here's how r is defined. R is the amount of displacement from the center of frame n-1 to the center of frame n, measured only in the xn direction. Let's look at some examples. The displacement from the center of frame 0 to the center of frame 1 is this vector shown here. I want to write the component of this vector that is only in the x1 direction. The component of this vector that is in the x1 direction, which is pointing to the right, is the link length A2. So I'll write A2 here in the table. Next, we can move on to r for the next row. R for the next row is the displacement from the center of frame 1 to the center of frame 2, measured only in the x2 direction. The displacement between these two frames is 0 because the center of the two frames are exactly on top of each other. So I write 0 in this place of the table. Okay, for the third row, r is the displacement from the center of frame 2 to the center of frame 3, measured only in the x3 direction. The displacement from the center of frame 2 to the center of frame 3 does not have any component in the x3 direction, so I write 0 in this place of the table. And we're finished with this parameter. Let's move on to the second displacement parameter, d. D is the amount of displacement from the center of frame n-1 to the center of frame n, measured only in the zn-1 direction. Let's look at some examples. For row 1, I substitute in n equals 1. So the d parameter here means the displacement from the center of frame 0 to the center of frame 1, measured only in the z0 direction. The component of this vector in the z0 direction is a1, so I'll write a1 in this part of the table. Next, let's do d for the second row. I substitute n equals 2 into the definition of the d parameter. D for row 2 is the displacement from the center of frame 1 to the center of frame 2, measured only in the z1 direction. Now here, filling in this parameter is very easy because the center of frame 2 is exactly in the same place as the center of frame 1. There is no displacement at all between the centers of these frames. So, since there is no displacement at all, the z component is also 0, and I fill in 0 in this place of the table. Lastly, let's do the third row. I substitute in n equals 3. D for the third row is the displacement from the center of frame 2 to the center of frame 3, measured only in the z2 direction. I have quite a few components of this vector to take into account. This displacement includes the link length A3, the link length A4, and also the joint variable D3. So in this part of the table, I'm going to write in A3 plus A4 plus D3. We've now finished filling out the table for this example.